Hi everybody, today we're talking about nested quantifiers. We're going to look at how the order of quantifiers changes the meaning of a statement. Nested quantifiers involve multiple levels of universal and existential quantifiers applied with logical expressions. For example, this statement, for every x there exists y, p of xy, means for every x we can find a value of y that satisfies the predicate p. As we're doing this, it's really important to remember that the order of the nested quantifiers really matters. Changing the order changes the meaning of the statement. So even though these statements look very similar, they don't mean the same thing. Let's take a closer look at our first statement. For every x there exists y, p of xy. In this statement, the value of y can depend on the choice of x. But when we look at our second statement, there exists x for every y, p of xy, means that one single value of x must work for every value of y. Let's look at that with an example. We'll use the predicate p of xy is y is greater than x over the domain of the reals. Now we'll use the nested quantifier for every x there exists y for p of xy, or this case y greater than x. This statement is true. Let's say x is 2. We could choose y to be 3. Or if x is 100, we can choose y to be 101. In general, we could choose y to be x plus 1. So the value of y could change depending on the value of x, but for every x we could find a y where y is greater than x. But if we flip the order of the quantifiers to there exists x for every y is greater than x, now x must be chosen first. The value of x can't change depending on the value of y. So let's say we pick a value of x, like x is equal to 10. Then this x has to make the predicate true for every value of y. So let's pick a value of y of 11. When we look at the statement 10 is greater than 11, we know that's false, which means our whole statement is false. Now let's find the truth value of a statement, but we're going to change up the domains. Our statement is there exists x for every y where y is less than or equal to x. Part A says our domain is 1, 2, 3, 4, 5. We want to know if we can pick a value of x such that it's greater than or equal to y for all values of y. And over our domain of D, this is true. If we let x be equal to 5, 5 is greater than or equal to every element in our domain of D. In part B, if we change our domain to the set of all integers, this is false because there's no greatest integer. I can't pick one single value of x that's greater than or equal to y for all y. Let's change our predicate to xy equals 1, and we're going to test for every x there exists y, xy equals 1. Part A starts with the domain of the integers. This is false because if we use the integer x is equal to 0, we can't find a y that makes 0 times y equal to 1. In part B, we're changing the domain to positive rational numbers. That means anything I can make as a fraction of two integers that are both positive. In this case, our statement is true because for any x, I can make y 1 over x, then x times 1 over x will be equal to 1. For our last example, we'll use the predicate p of xy equals x plus y equals 0, and we'll use the domain of the reals. We'll start with the statement for every x, for every y, p of xy. This says every value of x and every value of y together have a sum of 0. We know that's not true. As a counterexample, we could use 8 plus 2 does not equal 0. This shows us our statement is false. So let's try for every x there exists y, p of xy. This time, the statement is true. If we let y be negative x, then x plus negative x will always be 0. Now let's consider there exists x for every y, p of xy. This says we can set a value of x that when we add every value of y, we get 0. That's false. Say we pick our value of x to be 4. We could add 5, and 4 plus 5 does not equal 0, so our entire statement is not true. Then our final nested quantifier says there exists x, there exists y, p of xy. That means we can find a value of x and a value of y that makes this predicate true. So let's use x is 3, y is negative 3, then 3 plus negative 3 is 0. As you're working with nested quantifiers, remember that the order of the quantifiers determines the structure of the dependence in the statement. Changing the order doesn't just change wording, it changes the logical power of the statement by changing what information can be used when choosing your values.